So hi, I am Pawan Rawal. I've been leading the team which has been leading efforts on the GraphQL operations at Dgraph Labs. And over the years, we've received massive success in improving the performance of our software. And we'd like to share some of those techniques that we have used here in this real-world concurrent programming in Go workshop. With me is Ibrahim, who is the team lead of Dgraph Core, and Aman, who is a software engineer at Dgraph.
Hey everyone.
Hey folks.
Yeah. If you guys are on Twitter, you could follow me at Pawan underscore Rawal, and you can also follow Ibrahim at underscore I am Ibrahim. And if you guys like this workshop, feel free to send us a tweet or just post a tweet sharing your experience. That would be great. Finally, on to some housekeeping. This session would be recorded and published on Dgraph's YouTube channel. You can use the Q&A for questions, and we would be taking questions on first come, first serve basis. There are two ways of answering the question. We might decide to answer your question on the chat itself in the Q&A, or we might take it live. While I'm giving a talk, like Ibrahim and Aman would be monitoring the chat, and they would be looking at the questions and making sure that we answer all the questions that we have. Even though the workshop is scheduled for 1 hour, we would be happy to spend more time if there are more questions that come up. So feel free to ask questions, and we'll give you enough chances to ask your questions. And we definitely want to take all of your questions that come up. While talking to other members, please note that we do have a code of conduct that Aman would that Aman would share the link of in the chat. So we ask all of you to just be respectful of that while having your chat. But we do encourage chatting on the Zoom chat or asking questions. So please do that. Awesome. Uh, so let's move to what is Dgraph. This is like an introduction slide to tell you about Dgraph. Dgraph has organized this conference and also this workshop, and Ibrahim and me and Aman, all of us work at Dgraph. So Dgraph is a native GraphQL database with a graph backend which is written in Go. So most of the code that we write every day is written in Go. We use a lot of concurrent programming, and we have learned things that we just wanted to share, which is the purpose of this workshop. We are celebrating our 5 year anniversary. We started back in like December 2015, and it's been 5 years. So and it's been a great success because we've had a lot of traction on GitHub, 14,000 GitHub stars, 5 million Docker pulls, and Dgraph is a horizontally scalable and distributed GraphQL database. It's designed to scale to terabytes of data. It's also fault tolerant, provides ACID transactions and synchronous replication via Raft. So we have a lot of customers that have been able to improve the performance of their application using Dgraph, including Fortune 500 companies like Intel, Dell, and Comcast. Just to share a quote from one of our customers, Anthony Masters, this is what he had to write after using Dgraph. He says that I spent 6 months building a Graph API backend with the RDS database. After spending a week with Dgraph, we deleted 50,000 lines of code from our old API. The amount of work and time that Dgraph saves is simply unimaginable. So I hope that you guys also get a chance to try out Dgraph and are able to see the advantages of using it and are able to save some time and make things better for your customers. We are also the authors of BadgerDB, which is the most popular key value database written in Go. Badger uses a lot of concurrency concepts that we are also going to talk about in this workshop. So what we have done for you in this workshop is that we have pulled pieces of code from Badger, which show you some concurrency primitives, which you can use in your application straight away. Uh, Now that you understand what Dgraph does and the projects that we have worked on, let's get on to the agenda for this workshop. So we are going to talk about these things. We'll have a quick introduction to concurrency, in which we'll cover Go routines, channels, and some more things. After that, I'll walk you through a real-world problem in which we write a program that calculates the size of a directory. And we are going to look at two programs for this. One is going to be a version which doesn't have any concurrency. And then we'll see that how do we quickly modify it to make it concurrent. So in this example, we'll see how do we use Go routines and channels in like a real life example. After that, Ibrahim is going to present a couple of more very interesting use cases. One of them being throttling the number of Go routines in a program, and the other one being how do you shut down Go routines gracefully with closers. So people who have used Go routines would know that it's easy to start one, But when it comes to exiting a Go routine properly without losing any information, I think that's something that a lot of people who are working with Go routines first time miss. And we are going to show you like a very neat pattern that we have developed, which can help you do exactly that. Uh, so now we move on to like a quick introduction about Go routines and channels. So at Dgraph, we have had a lot of success by improving performance and reducing latency of our customers, and that's what that's what our customers are most delighted about. Concurrency primitives like Go routines and channels play a big role in us being able to achieve this. Let's see how you can use them to achieve similar results. If people here have used these primitives and would like to share how they use it, like you can type it out in a chat, and then uh, it will just give us more ideas about how you've used it. So in Go, each concurrently executing activity is called a Go routine, and channels are the connection between them. One of the most common examples is the net HTTP package. So people who have built servers in Go would know that when you start a server with the net HTTP package, it serves request concurrently. So that what that means is that if you have multiple clients hitting your server, one request would not wait for the other request to complete before being processed. So if you have like 50 concurrent requests, if you have 50 requests together, all of them would get started at the same time, and then they would be worked upon based upon the CPU that you have or based upon the capacity that's there. So that's a very simple example of how concurrency is already provided to you in Go, and we'll also be looking at some other ways of using concurrency. Go routines are cheaper than OS threads. That's because when they start with like a limited stack size, and then they grow based on the users that's needed. Whereas OS threads start with like they basically start with with like a bigger size on the stack. And this is something that Ibrahim would also touch upon, that even though Go routines are cheap, they are not free. That's why it's important to be mindful of how you use them. And then in terms of channels, like channels are the thing that you use to pass values between Go routines. There are two type of channels. There is buffered channel and then there's unbuffered channels. Unbuffered channels are also called synchronous channels because they're used to synchronize access between different Go routines. They don't have a capacity, but they're used to signal to they're basically used as a signaling mechanism between different Go routines. And then we have buffered channels, which are channels with capacity. So we're going to look into all these things, and this is just a quick intro to kind of give you an idea about what all different things we are going to cover. And some more examples that come to mind about using concurrency are that if you had to crawl a website, if you have to write a web crawler, then that's something that you could do concurrently. Like basically anytime that you have to perform network or disk IO, which are like small operations, that's when you can use concurrently and really get amazing performance improvements because of that. uh, and we do something similar at dgraph. So when at dgraph we solve or we resolve a graphql query, which is like a query in which there are like multiple fields, and then fields have children, we do all of it concurrently. So all the fields at one particular level are resolved concurrently, and then all the fields which are the child of a particular level are again resolved concurrently. So that's exactly how we are able to serve those requests in milliseconds. So now that we understand these basics, we'll move on to looking at a real world problem. The problem that we're going to solve here would be relatable to all of you. You all must have used you all must have used the command ls, which can tell you which can basically tell you the disk usage of a directory. So we are going to write something very similar. We are going to write a program which can, given a list of directories or given one directory, it can give you the total disk usage and the number of files in that directory. I have a diagram here which shows you what happens in the concurrent version of the code, but we'll come back to this later. For now, we are going to move on to looking at some code in which we see that how do we write a version which doesn't use any concurrency, and how do we write a version which uses concurrency, and what is the difference between the two, how much code do we have to change, and and what happens to what happens to the speed of the program, how much faster does the program become when we make it concurrent. So I'm going to share my editor here and we'll walk through this problem. So all of the code that I'm sharing here is available on GitHub, and we'll be sharing a link with you guys soon. So you can just look at it here, and you can just try to understand it, and you can ask questions about it. Or like after I'm done explaining the code, you can ask questions about it. You don't need to note it down. You don't need to worry about remembering any of this. Uh, so what we are looking at here is the first piece of code, which is a single version of it. I call it single because it doesn't use any goroutines. After we understand this, we'll be looking at the concurrent version as well. So this is a Go program in which we are passing the arguments of the program. So the way we would get the list of directories is through arguments. So when you run the program and pass a list of arguments, that's what we take as the initial set of directories that we want to calculate the size of. And we'll also be running this program later, but just trying to explain to you what happens here. And after that, once we have the initial root set of directories, then we call this function called walk directory on each of them. So for every directory that we see here, we call the function walk directory. And all of this is happening serially. All of this is happening one by one. We are not using any concurrency here. It's like a simple recursive program that we are walking over. So we call walk directory on like a root program, and then let's go look at walk directory. So you would notice that I have a sleep statement here. We'll get into why I have this here a bit later, but let's first understand the rest of the program. So what I'm doing is given a directory, I'm calling this function called dir ends. And what dir ends does is that it just gives me out all the entries in the program, or like all the entries in the directory. So when I say entries, then this could be files or this could be other directories within this directory. So say if I was to run this on a directory, then dir ends would give me back all the files and all the directories in that directory. So by doing this, all that I'm doing is I'm doing like a walk across my directory structure for which I want to calculate the file size. So after getting an entry, I check if it is a directory, then I call the walk directory program again recursively to walk that particular subdirectory and get the number of files and the total size of files in that directory. And I would append it to my return values here. My walk directory is returning the number of files that it has found and the size of all the files that it has found. So if my entry is a directory, I would walk over it, I would get the files, and I would append it to this global number, which is the num files and the size. Or else, if it's a file itself, then I would just then I would just increase the size by the entry dot size, and I would increase the number of files. So just by doing this, I can walk over my directory recursively and get the total size and the number of files in that directory. And the reason, like now going back to the sleep, the reason that I have the sleep is that this sleep is going to make it very apparent as to what is the difference between this program and the concurrent version of the program. Because my laptop doesn't have a lot of disk space, so I am only able to run this on something which has say like I'll basically be running this on a directory which has 60 gigabytes of space. So on that program, when you add this sleep, you can really see that how much of a difference is made by this concurrent versus the single version program. If you had a slow operation, then then this particular difference would be obvious without the sleep as well. So now that we understand this simple single-threaded version, I'll move on to showing the concurrent version and how many, like how simple it is and how simply can we just make some changes here, and and just show you like how we are able to improve the performance. So I'll just have both of these side by side to show you the differences. But all that we are doing here is that we initiated a channel, which is a channel of type int64. And this is the channel that we would be sending the file sizes on. So earlier we were returning the file sizes from the function. Now we would be using this channel to communicate the file size between different coroutines. Another thing we have here is the sync wait group. Sync wait group is a very useful thing when you have a use case in which you want to start multiple go routines and wait for all of them to finish. So that's what exactly we are doing here. We are adding an element to the wait group saying that we are going to start a new go routine. And then we start the go routine for the root directory. And while calling walk directory, you can see that I have appended go in front of it, which means that we are calling it as a go routine and not just like a normal function. So we pass the root directory, we pass the wait group because we want to also tell that when the function is done, we want to mark the wait group as done there, and then we pass the file sizes channel. So this is like these are the changes that instead of returning the values, now we pass a channel onto which we get the values. We also pass the sync wait group, which would tell us that this function is done. So now we can have a look at the walk directory function, and then we'll come back and see what else is happening here. So the walk directory function, it still has a time dot sleep. There are two or three things which have changed here. One is that we're calling defer end dot done. What this does is that once this function is done and it's about to exit, it would call the wait group dot done. And what that does is that it would tell the parent coroutine, which is the main coroutine, that one of the functions which was a coroutine is now done. And this would be useful when we have to wait for all of the coroutines to finish. Apart from that, the dir ends function is pretty much the same. And what we are doing is that if we encounter a directory, we just instead of running it as like a function inline using walk directory, we call it in a go routine, because this is again something which can be done independently, which can be done concurrently. Like anytime you have a problem in which you can break things down which are independent and which can be done concurrently, that's where you use a go routine. So I have added a counter to the wait group, and then I'm calling go walk directory. And this is the case when we encounter a file. So when we encounter a file, then we just return the size of that file. We just push it onto the file sizes channel. So this file sizes channel would get the size of all the files, and then we would read over those when we are in the main coroutine. This would also become more clear once I share the diagram, which I'll be moving to in actually now, because that will give more of an idea as to what's happening here. So as you can see this diagram, what's happening is that we have the main go routine, and inside the main go routine, we call walk directory, which is called in go routines. And those walk directory go routines also themselves call walk directory on their child subdirectories. All of these are sending the size on a file sizes channel. And this file sizes channel is the one that we read in the main go routine to basically to essentially aggregate the sum of all the files that we have seen. So this is what is happening. This channel is common across all the go routines, across the walk directory go routine, across the main go routine, and all of the go routines are sending their values on this, and the main go routine just reads this. Uh, let's move back to some code and see some more interesting bits uh, here. So one more interesting thing that we're using here is a semaphore. So we are implementing a semaphore here. So this dir ends function, it has a semaphore. Semaphore is a mechanism that you can use to limit the number of concurrent invocations of a function. So the reason we are doing this here is that, as you can see, we are reading a directory here. And when we are reading a directory, we need to have a file descriptor. So just to make sure that we don't end up like reading too many directories and basically blowing out our file descriptor limit, we have some rate limiting here. This is just one of the ways of doing rate limiting. It's a very primitive, it's a very easy way of doing it. This approach also has some problems in which we are not handling errors. So that is something that Ibrahim would be covering in his talk, in which he shows more sophisticated and better ways of doing rate limiting. But this is like a simple primitive approach that you can take, which is to have like a buffered channel. So every time that you start the dir ends function, you send an entry on the buffered channel, and every time you're done with it, then you basically read from the channel. What this would make sure is that at any time there are only 20 invocations of the dir ends channel and not more. So this is what is happening here. Like, we are using a buffer channel for doing a semaphore. We are using channels and wait groups for walking over directories. And then finally, in the main function, what we do is we have a go routine that's waiting for the wait group to come back, for all the go routines to come back. And then it's going to close the file sizes channel. So this go routine is again running concurrently, even though it's in the main go routine here. And we are reading over the file sizes channel, and we are accumulating the results. And only when all the wait groups have returned, then we would close the file sizes channel, at which point this loop would also end, and it would print the total time taken and the disk usage that we see. Uh, so what we'll do now is that I'll share my terminal and I'll actually show like an invocation of the program and show how it's different uh, when we use the concurrent version versus the single version. After this, I'm going to start taking questions, but just wanted to show you how massive difference can it make when you use the concurrent version. So I'm here in this folder in which I'm going to check that how much time does it take for calculating the size of a directory. I have a folder called dump which has like 56 GB of data. So I'm running it first with the single version and let's see how much time does it take. And let's see what is the result that it prints out. It's taking a long time as expected because we are not using concurrency when we should be. So it took like 9.77 seconds to calculate approximately 10,000 files with a total data of 56.6 GB. Now let's look at the concurrent version. Remember, it took like approximately 10 seconds to do this job. So do you guys want to guess how much time would it take in the concurrent version? Let's look at it. Well, it took 703 milliseconds. That's like if you compare the performance, it's probably 15 times less the time that it took in the concurrent version to do the same thing that it took in the single threaded version. So looking at something like this, you can see that what is the performance gain that you can get out of using concurrency in your applications. And this is something that you should be looking into if you're not already looking at it. Like anytime that you're doing a network IO or you're doing like a disk IO, using concurrency can actually give you massive gains. Awesome. So I think at this point, I like we can wait and see if we have any questions. Aman, do we have any questions that we'd like to take at this point? I think Aman, you're muted.
No problem, we don't have any.
Okay, okay. So I think I'm like I'll probably hand it over to Ibrahim, who is someone who actually writes and debugs concurrent code daily and is very good at it. And he's going to walk you guys over a couple of interesting use cases that he has used and that he would like to share about how he solves problems at Dgraph and in Badger. Over to you, Ibrahim.
Thanks, Pawan. Let me share my screen. All right, I hope you guys can see my screen. So let me introduce myself. My name is Ibrahim Jarif. I am a tech lead / manager at Dgraph Labs. I take care of a team that works on Dgraph core. So we take care of Badger, y.Throttle, and Dgraph itself. My day-to-day job involves creating a lot of goroutines and debugging why they do not work. So my goal over here is to explain what we have learned. So there are a lot of learnings, and I don't think I can do that in 30 minutes, but my goal here is to explain 2 items or 2 techniques that we have learned and how we use them at Dgraph and how you could use them in your code, right? So Pawan gave a very nice introduction to concurrency. So you have goroutines which make things faster, right? But making things fast is not the only goal you should have. For instance, you create something and it runs fast, but then there are other side effects for it. For instance, let's say you write a program, right? Pawan had a walkdir function. The walkdir function walks to a directory and collects some data. Let's say that walkdir function was not bounded, right? In Pawan's example, there was a semaphore. You remove that semaphore, what would happen is you would keep on creating goroutines, right? And even though Pawan mentioned that the goroutines are cheap, they are definitely not free, right? So every time you create a goroutine, it comes with an associated cost with it. Think of this in terms of a database, right? A database does a lot of things in the background. For instance, Badger. Badger has compactions, which always run in the background, right? Compactions move stuff, it compacts the LSMP, but it does some work. So if we do not bound these goroutines, let's say you just keep running this goroutine, what would happen is at some point you would have too many of these goroutines, and that would affect your memory. It would affect your CPU as well. So even though you want your program to be fast, you do not want it to be just fast, right? You have to be careful about how you're creating goroutines, what goroutines are running as well. So I'm going to show you 2 techniques. Both of them are around goroutine. The first thing we'll look at is a throttle type that we use to limit the number of goroutines. I'll show you a demo of how we do that. And followed by that, I'll show you how do you gracefully stop goroutines, right? So starting a goroutine is as simple as adding the go keyword, right? But you have to be careful about stopping it as well, right? So before we go into that, before we go into throttle type and closer, I'd like to show you a quick example of what happens if you do not have, if you don't limit stuff, right? So you start a program which does not have any kind of limitation. So please let me know in the chat if this is not readable. I am hoping you guys can read it. So what I'm going to do is I am going to show you guys an example. So let's look at the code first, then I'll run it, right? So what I'm going to do is I'm going to open the code. So what I have over here is, give me 1 second. I hope it's visible. So what I have on the left-hand side is a very simple program. What I'm doing is, this is my main function where the execution starts. I start a goroutine, which is called print starts. And what this guy does is, it's gonna run an infinite loop. And after every 500 milliseconds, it is just gonna tell me how many goroutines are running. This num goroutine function is gonna tell me how many goroutines are running. So that's what it does. And then what I do is, in a for loop over here, I do some kind of processing. Let's just assume this is doing some work, right? So we process items, and then I just call this function in a background goroutine. And to keep this example simple, I do not do any work. I just call it time.sleep, which just means that simulate some work which took 1 second, right? So that's all this program does. And then I wait for 2 seconds just to show this output, right? Without this time.sleep, my program wouldn't even show any output. So if I run this, what happens is, if you see my for loop plan as quickly as it could, it started all the go routines. So over here at this point, this print tells me that there were 102 go routines active. So if these many go routines are active, that also means that the work they were doing was active, right? So if this was Badger or Dgraph, this also means that we started doing a lot of work in the background, which might not always be what you want. You want to do work, but you might also want to have limits on how much work do you do. So this is exactly what we'll try to solve, and then I'll walk you through an example. I'll show you what do we use and how do we do that. So moving on. So now what we'll do is we'll look at throttle type. This is nothing special. It's a type that we use internally at Dgraph to limit the number of coroutines. So this is what it looks like. It's a very straightforward type. What it does is it has a wait group, which allows me to wait for things. It has a channel, which acts as a gatekeeper. And there's an error channel, which allows me to catch any errors that happen in the background goroutine as well. So in the example that Pawan showed, we had a SEMA channel, right? SEMA channel, which was a buffered channel. That SEMA channel acted as a gatekeeper, but the problem was that we weren't handling any of the errors over there. So this type just allows us to encapsulate all those properties in a simple type, which can be used everywhere. So this, if you search for this type across Badger or Dgraph, you would find multiple instances where we use it. So if you guys want to look at it, it's located in Badger/y package. So it's in y.go file. So let me show you an example of what this throttle type does. So let's go back to the editor. I'm just going to go to throttle. So before you look at the code, I'd like to run this and show you what it behaves like, right? So we noticed that the one without any limitations just started 100 goroutines and just tried to do everything it possibly can. In this one, if I run this one, if you notice, active number of goroutines is stable. So I have 5 over here. I still have 5. If you notice, we are even processing slowly. So when you're adding goroutines, your goal should not be to just make it fast. Your goal should be to make it fast, considering other aspects as well, right? So in my case, if this do work function, whatever work I'm doing was expensive, right? Maybe it takes 2 GB of memory for any reason, then I should take care of ensuring that I do not blow up the memory by just creating goroutines blindly. So this is what throttle type does. It's limiting the number of goroutines. So let me show you what it does and how it does that, right? So the code on the right-hand side is what was running. So I'll walk you through, and then I'll walk you through what this code does, and then we'll look at how this throttle type is implemented and what it does. So we still have the print stats, which was running in the background, and it's printing the number of goroutines. So on the left-hand side, we are printing the number of goroutines over here. Followed by that, I still have the for loop in which I'm doing some work. But the interesting bit over here is the throttle type. I create a new variable of that type. Before starting a goroutine, I call throttle.do. So this is what my new type gives me. My new type gives me 2 methods, 3 methods actually, 3 important ones. First one is called throttle.do, which acts as a gatekeeper. So if I call throttle.do, what the underlying type would do, that it would check how many goroutines are running. If it is running more than X number, then it would not let this caller pass through. So at this line, we get blocked. So in my case, that X number where we stop is 3 over here. So when I create this new throttle, I mention over here that I want to run only 3 concurrent or 3 goroutines at any given point of time. So this throttle, so when this loop starts for the 4th iteration, it's going to get blocked over here. So this means that we'll always have at max 3 doer goroutines running. If you notice on the left hand side, it says 5, right? So you might be wondering, why is there 5 when we have set 3 over here? But remember that we started a goroutine for print stats. So that's the 4th goroutine. And then the main function also runs in a goroutine. So that counts as 1. So you have 3 goroutines running because of this throttle, 1 because of the sprint stats, and 1 because of this main function. So how you use this throttle is once you are able to pass through this line, which means that there are less goroutines running than what you want to run, you start executing your goroutine. But what you also do is you pass this throttle object over here. So this th that you see is the throttle that we created, right? So our goal here is to block the active block more than 3 goroutines to run. But what we also want is we want to know if the existing goroutines are finished, right? So this throttle type, what we do is we pass this throttle type to this worker over here, as in the doer gets the throttle type. And if you notice that in my throttle type, I have this defer, right? So when this do work simulates a job, sleeps for 1 second, and when it's done, it's going to call throttle.done, which means that, hey, I'm done doing my work, let the other guy pass through. So then the 4th person or whoever was blocked on this line gets unblocked, and then it starts working. So this is how it gets blocked. And as I mentioned, right, the benefit over here is that you want to limit. What that limit should be is a tough question to answer, right? There's no simple answer to how many goroutines do you want to run. You need to figure that out by either benchmarking or profiling, right? You would run a profile and you would look at, do I have more goroutines? Do I have more memory being used by these goroutines? And then you can figure out. So there's no straightforward answer to what this number should be. This depends on what kind of work you're doing and what this throttle type is doing. At the end, what you do is you just call throttle.finish, which just means that wait for everything to finish. So this over here, we get blocked on this line until every goroutine that had received this throttle calls it done on it. So it just means that we wait for all the goroutines to finish. Another important thing to notice over here is I'm not handling the errors over here. For the sake of simplicity, I've skipped error handling. This do function is gonna return an error. So if I quickly go into do function, if you notice it returns an error. I'll explain what this function does later, but notice that it returns the error over here. But this means that if I started 10 goroutines, let's say there were 10 do work goroutines running, even if one of them gives me an error saying that, hey, I could not do this work, all the before starting the other goroutines, this do is going to give me that error, which just means that, hey, the other goroutine that was already running has failed. You might want to either look at that failure, or you might want to just exit, or you might want to skip that. So this throttle gives me that, and so does this finish. So this finish also gives me back an error, which just means that the background goroutine finished successfully or not. So this is the gist of what this throttle type does. Before I go into the details of how do we use this or how is this implemented, do we have any questions? I'll be happy to take those now.
Yes, Ibrahim. So we have one question. So one of our participants would like to know, different strategies we have to test our concurrent code.
Right. That's a pretty interesting question, right? So I think there are 2 ways, maybe 3 ways of doing this. First one would be, there are kinds of problem what you're looking for. So you need to figure out what you're trying to test, right? In concurrent programs, you would have race condition. That's a majority of your programs. The first bug that you would encounter usually is the race condition. So this Golang provides a very nice flag for this. So if I want to run something, let's say I have this program, right? So what I can do is I can do go run. I can use this flag, which just says that run my program with this race flag. When you add this, Golang will automatically look for race condition. So if, let's say I do something, right? So to demo that, what I'm going to do is I'm just going to do where x is an integer. Oops, and then oops. Okay, integer. And what I do is I do I do a equals I, I'm going to read that value and I'm going to do I plus plus. Oops, sorry, x plus plus. This is going to be x. So I do x plus plus. So over here, what I'm doing is, and just to make the compiler happy, I'm just going to do a. So I'm not doing any work. All that I'm trying to do is I'm just trying to access this variable. I'm reading the value of x, which is common for all the goroutines. Okay, that's important. It's common for all the goroutines. And then I'm incrementing its value. So now if I run this program, right, so I just built, oops, let me run it this way. So if I run this, notice what Golang tells me. Golang tells me that there's a data race. There's a data race on these lines. So this is pretty neat. So this is one way. This is one kind of bug that you would mostly see in concurrent programs, that there's a race condition, and Golang helps you do that. There are other ways as well. For instance, if you're trying to test concurrent programs, you might want to structure your test that way. You might want to use atomics and then some channels, some handling around those to test them. If you're benchmarking something, so there are two kinds of benchmarks as well. You have a simple benchmark and there's a concurrent benchmark as well. So I don't have a demo for that, but if you Google for Golang concurrent benchmark, you would come across the benchmark type, which would tell you that there's a bench dot, there's a pb.next type, which allows you to write concurrent benchmarks as well. So these are sort of the things that you would do to, test and benchmark your code, your parallel code. Do we have more questions? All right, so let's move on. So let me explain what this throttle type does actually. So if I go inside this throttle type, this is similar to what Pawan had. There's nothing special over here. It's just how we handle it, right? So what I have over here is I have a channel. This is a buffered channel. What this allows me to do is this limits the number of active goroutines. So this max is what the user would give me. It will tell me that run 3 goroutines, and I would create this channel with max size of 3. And then this channel would act as my gatekeeper. So if this channel has capacity, I let that goroutine pass. If not, I would stop. I also create an error channel. Why? Because I would like to catch all the errors that show up while running any of the goroutines as well. This is really important. So let's say you're doing background job and your network goes down. So if you're not handling this error, and let's say you're doing something in background, that background thread, all the background threads would keep running, right? You would not have a way to catch that error. So this is really important to have an error channel wherein you would know that your background threads are failed as well. So that's what new throttle does. Let me show you what do does. So do was the gatekeeper, right? So this do function is a gatekeeper, which will either let you pass or it will stop you over there that, hey, there are already maximum goroutines running. Do not go ahead of this. So if you look at this, this is a for select. For select is a pretty common technique for having doing some work either on which you get blocked or you make progress. So over here, if you see, this is the channel, this is the buffered channel that we had created. So what this line does is it tries to push an event. Let's say it tries to push a struct into that channel. If you already have maximum goroutine running, you would get blocked over here. If you say maximum 3 and you already have 3 goroutines running, you get blocked over here. If not, the event is pushed into this channel and then you add it to a wait group and then you return from here, which just means that you are allowed to start this goroutine. So this is the interesting bit of this throttle, wherein you stop if there's already enough goroutines running. If not, you pause it. What we also do is we keep looking at the error channel as well. So if this error channel has an event, which means someone who ran before we call this do has failed. So in that case, we would have this error over here, and then we can handle this error in the caller, in the main thread. So there's this done function. This done function is what a goroutine would call when it finishes its execution. So this is where it signals to the throttle type that, hey, I'm done using this throttle. Now you can let the other guy pass. What it does is it just pulls out one event from that buffer channel so that we have space for a new event. It also pushes an error if you have an error, right? If let's say you mentioned that something is failing, so we push an error over here. And then it just marks the wait group as done, which also helps us when we call the finish on the throttle type, because this helps us figure out how many goroutines are currently running. And the last function that we have was finished. If I go back to my example, if you notice, I had this finish over, right, wherein we wait for everything to finish. So finish is pretty simple as well. We wait for everyone that was running to finish. We close the 2 buffered channels that we had. And then what we do is we drain the error channel. this error channel might have some errors from the last batch of coroutines that we're running. So if we find an error, we set that error and then we just return that error to the caller so that the caller gets to know that, yes, this batch of jobs failed. So this is a pretty simple type, but we use this type or in everywhere in Badger and Dgraph. If you search for throttle, you would realize that this very simple type is very effective. It allows us to limit goroutines and we use it all over the place in Badger and Dgraph. Do we have any questions on this?
Yes, Ibrahim. So we have a few questions. So one of our participants has asked, so what would be a real world max int for a new throttle? Because in the example we have taken up 3, so can it be something which can be increased?
So let's say we look at this example, right, where I just have this do work in which I'm not doing any work, right? So this number that I have 3 over here, this number depends on the kind of work you're doing. So let's look at the example I have currently open. So if I go to do work, that's not doing any work, right? It's just going to sleep. So this guy is not using CPU. This guy is not using a lot of memory as well. It's only using a few KBs of what stack this goroutine gets. So in this case, what I can do is I can have a big number. I can have big number as 1 million as well. Why? Because the kind of work that I'm doing is very small. It's short-lived. It does not need a lot of CPU. It does not need a lot of RAM. But let's say you are reading a file. You're reading chunks of 100 MB from a file parallelly through goroutines. In that case, if you set this number to 1 million, what it means is that you start 1 million goroutines. Each goroutine is reading 100 MB of data. So you would have a lot of active data in the RAM. So what I'm trying to explain is that this number, there's no easy way to figure out this number. This number depends on the nature of work you're doing. If you're doing short-lived work, which does not take a lot of RAM, you could use more goroutines. If you have more CPU as well, right? It also depends on how many CPUs you have. So you could use more goroutines. If you have expensive work, if you have something that's CPU bound, if you have something that takes a lot of RAM, you might want to go slow on this number. You might need to write a test, you might need to profile a code to figure out at what point you get the best performance.
We also have one more question. So one of our participants asked, is there any pattern for dynamically scaling number of Go routines, or maybe scaling it down when there is more work?
Yes, there are definitely ways to do this, but it might not be as straightforward as using a throttle type, right? So what you can do is there are multiple ways to do this as well. So first you have to figure out when do you want to scale it down. So if your goal is to scale it down when the memory has high pressure, then you might need to figure out. So what you can do is you can keep monitoring the memory pressure, and then this throttle type does not support it right now, but it's pretty easy to add it as well, right? If you look at this channel is what acts as a gatekeeper. So if you want this throttle type to be able to increase, to be dynamically resizable, what you would need is you would need the ability to resize this channel, but you have to be careful that you cannot do that directly as well, because creating a channel, creating a new channel for this variable would also cause race conditions if you try to do at runtime. So you would need to carefully have locks to increase the size of this, but you can definitely do that. I don't have a demo for that, but yes, that's definitely possible. You just have to figure out a way to monitor your RAM or your CPU, and then this throttle type, or even if you have a simple channel, right? You use a channel as a buffered way, a gatekeeper, then you can just increase the size of that channel or decrease the size, and that would act as a dynamic rate limiter.
I think one thing, Ibrahim, is also to consider, like, why do you need to do that, right? I think a
Yes.
goroutine which is around doesn't cost you much. It's just around. It's not going to take any more resources. So it's different from a typical thread pool where each thread is sort of more expensive. Goroutine is very lightweight. So you probably don't need to scale them up. You can just decide how many goroutines you want up front, and you have a channel to distribute work. And if they don't have any work, they would not do anything.
Yes, that's correct as well. Yes. All right. I think we can move on to the next part. So this was the throttle type, which allows us to limit the number of coroutines, right? I mentioned there are two things I want to show. So this throttle was the first bit. The second one is something called as closer. This is what we actively use at Dgraph, in Dgraph and Badger as well. So one of the common issues you would see with goroutine is that you start a goroutine, but you do not stop it. You do not gracefully stop it. So let's say you open a file, or let's say you have a network connection in a goroutine, you're doing some work, but when your program ends, you would want to signal or you would want to gracefully shut down that connection, right? So this is also something that we have to do on everywhere. So to do this, we have this type called closer, right? So closer, similar to throttle, is not really a complicated type, but it's a very useful type. So I'm going to show a demo of what this does and how we use this closer to stop goroutines gracefully. So this closer type is taken from Ristrato. So you could go to Ristrato and look at the Z package. This has this closer type. So let me show you a quick demo of what closer does and why would you need it. Right, so the code on the right-hand side is what I'm going to run right now. So it's similar to what we had earlier, but the important bit to notice over here that in my previous example, the do work go routine would just die when the program ends. Over here, my goal is to gracefully stop this go routine. My goal is to start a go routine, let it do some work, signal it to stop, wait for it to gracefully stop, and then end my program. So let me run this. So let me run this first. What I'll do is I'll just run this one. So right now what is going on is my main thread started. This do work goroutine was called. It's running right now and it's just simulating some work. So I just have a time.sleep over here and it's processing some items. Now let's say I want to stop it for some reason. So what I can do is I can press Control C. If you notice over here that this print statement was printed from my goroutine over here, and then it returns from here, which means that my goroutine exited gracefully. This is useful when you want to maybe close an active connection, you want to close a file descriptor, you want to do some cleanup task while finishing the goroutine, right? So this is, for instance, in Badger, when the DB is closed, what we do is we close all the files, we truncate some files, we do some compaction. So this closer helps us deal with that. So let me show you what this program does. As I mentioned earlier, my goal is to start a goroutine, signal it to stop, and then wait for it to finish. So over here, what I do is I use this closer to do that. So this closer, I create a new object of a closer. I pass this closer to do work. Let me show you what do work does. So this do work again uses the for select pattern, right, which I showed in my previous example. So this closer is what we pass to do work. It's going to keep doing some work. So this is a select case, right, wherein you would either execute this one or this one. But so since I've just started this closer, this is gonna this channel. This is a function which gives you back a value, but this is not going to give you back any value initially. I'll explain how this works later, but let's just assume it's not returning any value right now. So you keep executing this default case wherein you are doing some work, and when I press Control C, when I pressed Control C in this example, when I do a Control C over here, I have some code which handles that Control C and then signals the algorithm to stop. So if I go down, this piece of code is going to catch that signal, that integer, that sigint, that Control C that I pressed. It's going to notify the goroutine to stop. So this cl.signal essentially notifies the goroutine to stop that, hey, that there's some event that has occurred and you need to stop. So this, as soon as this is triggered, this line that was earlier not being executed, that was earlier not returning an event, will quickly return an event saying that yes, that there is an event and I've been asked to shut down, that this closure has been closed because the signal was called. And then we know that we have to exit over here, so we do some cleanup operations and then return from here. And then towards the end, I have the cl.wait. So notice the cl was what I created over here. I passed it to my worker. When I receive an event, I signal it to exit, and then I wait for it to exit. So this cl.wait will get blocked until this goroutine finishes. So the cl.wait on this line, the highlighted line is going to get blocked until this do work goroutine finishes. So this is what closure actually does, right? So in this example, I just have one goroutine, but even if I have, let's say 3 goroutines, 4 goroutines, this closure can be used to signal to ask to stop all of them at once. So I can just do, instead of doing one, what I can do is I can make this 2. And then if I have 2 goroutines over here, when I do signal over here, this call is going to stop both the goroutines, and then this call will wait. This line would get blocked until both the goroutine finishes. So this is the gist of what closer does. This is also a very important type that we have. This allows us to handle goroutines much more better than what we would do it without this. If there are questions, I could take those before diving into the implementation of new closer, the closer type.
I think there's a question that we are seeing repeatedly, which is that why would you use a closer and why not just use a context? The reason is that you can cancel a context, but a context would not tell you that the goroutine which was executing work has finished gracefully. It would just tell the goroutine that this context has been canceled, and the goroutine doesn't handle it immediately, or there's a delay, which there would always be. If there's a bit of a delay, then the goroutine would still be running, but your main caller would have returned because it has canceled the context, and that leads to like race conditions. That could lead to race conditions in the code base, which is why closer was created to be able to not only signal, that means cancel the context, but also wait for the goroutines, whichever were spun out, to finish before the caller returns back. So that's the difference between context and closer. Closer actually uses context internally, but it does more things on top of it.
Yes, and that waiting bit is pretty important, right? If you cancel something, at times there will be times wherein you want to wait for it to finish as well, that you have signaled it to cancel, but then you don't know if it has actually finished. If you had a tight for loop somewhere, then it could be happening that your goroutine hasn't, even though you have signaled it, that goroutine is not stopping, or it would stop after a second. So you would need a way to wait for it as well. So closer does exactly that. It allows you to stop them and then wait for them to finish, so that you know that whatever signal you have sent has been handled on the goroutine and it has finished. So that's what closer is. So let me walk you guys through some of the APIs, right? So closer has a wait group, and then it has a context. So this context is used to cancel. This is used to send cancellation signals to the goroutines. And this wait group is used to wait for those goroutines to finish. So when you call new closer, so if I go back to my code, I just new closer. So when you call new closer, what happens is we just create a new context for you, but with a cancellation. This cancellation allows us to signal that the goroutines have finished and they should stop, but it also creates a wait group for us. Apart from this, we also this has been closed function, right? So if you notice, it returns a channel, and what happens is that if you haven't called the signal function yet, this closer.signal, which means you haven't canceled anything yet, this function will not return. So this is a channel from which you're trying to pull a value. So this, if you call has been closed before you have closed things, it would get blocked over here. So this is the line. So if I go back to my code as well, there's this line, and this line gets blocked over here. So this line would not get executed until the channel has been closed and we have an event to pull from here. So that's what this function does. It allows us to wait for that event. As soon as you cancel something, you will have an event over here, and then this channel will give you back a value, and then you can handle this closer or handle your cleanup operations gracefully. And then we have this wait function. Wait function essentially just waits for the underlying wait group. So you signal something, your general pattern would be start a goroutine and signal it to wait, and then you wait for it to finish. So this is where you would wait for it. This is what I was doing in my example as well. So if I show you towards the end, I signal it over here when I get an event, but then I wait for it to finish as well. And then we have another helper function as well, which just allows us to do both the stuff at the same time. The signal and wait, which signals it to stop and then waits for it to complete. So yeah, this is what closer is. This is similar to throttle, but the utility of this type is a lot more. We use this all over the place. We use this to gracefully handle goroutines in Azure and Dgraph. So this is all I had. If there are questions, I can take those now.
There are actually a lot of questions here.
Yeah, we have a lot of questions.
Okay, I can take those questions.
Cool. So I think one of the questions is that people are talking about this package which does weighted semaphore in Xsync. So there's a package in Xsync called weighted semaphore, and someone is asking that how is that different from what we do here in the implementation of throttle that we said. Do you know about that package, Ibrahim?
No, I haven't tried it, but I can look at that and maybe get back with an answer.
Okay.
I
Also,
know
we
there's
have
an error
one,
group.
so we have one other question where people are asking about worker our experience with worker pool and versus the go routines. So
Yeah.
Right, right.
I mean, Go doesn't have a worker pool, right, per se. So you can use a channel to create tasks and then create a bunch of goroutines which are pulling from the channel each task and executing that task, and that's a common pattern in Go. Um, but I think a throttle actually does more, right? A throttle can be used to uh, you like you're not limited to the channel and go routine scenario. You can actually like use that scenario, but you can also like do more things where you shoot off some task and you just wait for it towards the end, you know.
Right. Do we have more questions, Aman?
yeah, so we have one more question, which is more around our use of throttle. So the basic question is y.Throttle a mixture of sync.semaphore and error groups, the way we are using it?
Yes, I would say, I mean, I'll have to check what sync.WaitGroup does actually, but error group essentially allows you to stop when a routine errors out, right? So yes, I mean, yes, the error group allows you to handle errors, and throttle also allows you to handle errors, but it also allows you to limit the number of routines.
There's also a question asking that if these packages and APIs are available as a Go module, it's something that I can answer. Yes, yes, yes. These packages are available, and we'll also be sharing links. Like these packages are there in Badger and Ristretto. So all of these packages are there for you, and you can use them directly.
Right, so there's this Y package in Badger, which has a bunch of utility functions. If you go to this y.go, if you guys can see my screen, inside over here, there is the throttle type. You see, this is the throttle type. So you can definitely import this Y package. This is a complete package, right? So you can just import the Badger/Y package and use the throttle type. And the same goes for the closer as well. It's in Ristretto/Z package.
Actually,
Another
some of
question
these we
is,
can move out to the Z package in Illustrator as well, because that's where we are moving a lot of the common code between Dgraph and Badger. So we could move some of these Y stuff out to Z.
Yes, yes, definitely. I
there's one
think,
more.
yeah,
Sorry,
go
go
ahead,
ahead.
Pawan. Yeah.
I was going to move on to another question.
Okay, I can take
Yeah.
that.
Yeah. So the question is that concurrency is great, but how does this translate to how end user on dgraph controls this? If a user wants to look at multiple years or multiple months of data, any introspection how this query would be run?
So if I understand the question correctly, the question would be, does the user want to figure out how does the user want to configure the concurrency? Is that the question? Or can they
So the user
inspect
is
how the
asking,
concurrency is behaving?
yeah, like how exactly does concurrency help in in terms of the end user and how it helps in dgraph and how a query is run in that sense.
I see, I see. So let me try to answer this. So Dgraph has something called the bulk loader, right? Bulk loader is what people use to import large amount of data into Dgraph. Bulk loader behind the scenes uses a lot of goroutines. So even though the user does not know,
Yeah.
it's invisible for the user, but behind the scenes, what we do is we start a bunch of goroutines, we move some data around and try to insert the data at a faster rate. There is also, Badger also has a stream framework, right? The stream framework is what we use to move data. Dgraph does snapshot transfer or predicate movements, right? The sharding. So for all those cases, we use stream framework, and stream framework behind the scenes uses goroutines to move that data. So for the user, they might not really know there's something going on in the background, but Dgraph uses goroutines for that. For your queries as well, when you send a query, what would happen is in the background, Dgraph would try to process it parallelly. We run a bunch of goroutines, we split that query up into subsections, and then we try to process it. And I think that's what Pawan was trying to demonstrate as well in his file example, wherein that disk usage example was a simple one, but in Dgraph, we do something similar. We have a tree, a hierarchy of things that we need to resolve. What we'll do is we'll create a bunch of goroutines, and then each goroutine is going to try to resolve its own section. And because of that, we get faster query times with Dgraph.
Yeah. That's exactly what we do while we're resolving a query. Like if you're an end user, you basically don't need to worry about the concurrency and number of goroutines. We handle that for you, and we increase it according to whatever we need, according to your query. But you are able to get the best performance because we use concurrency well in Dgraph and Bazel.
Yes, that's correct. All right, I think
There
if
are
there are
still
no
some more
more
questions. There are still
we have
some
more
more
questions.
questions coming in. One question is that would really appreciate if you guys can briefly touch upon difficulties you face while working with concurrency in Go.
Um, I don't have an example specifically for Go, but let's say concurrency is hard to debug in general. So you start Go routines, you have Go routines that are communicating with each other, you're sending data around, and then you would have a hard time trying to figure out what's going on where. If you have a single threaded program, you can add print statements and figure out. With concurrency, that problem becomes much more complex, wherein you have data that's moving around, and then it's difficult to figure out what's happening where. So yeah, Manish, do you have any additions to this?
Concurrency is hard. Concurrency is hard. I think people think memory management is hard. I think concurrency is hard too. Um, and we have had like a lot of issues, right? We have seen I think somebody's asking about goroutine weeks. We have seen goroutine weeks where we exited early and did not wait for example, each coroutine was pushing to an error channel when they were done, and the error channel did not have enough capacity, and so we saw the first error and we returned from the caller, but the others were still waiting for pushing to the error channel, and so they were left around. So we have seen coroutine leaks. We have used sync.pool extensively because of the to be able to deal with memory better. And we have seen corruptions because we pushed something to sync.pool, but then ended up still using it afterwards, and somebody else, some other goroutine was also using it. And so we have seen those. So
I think there are memory issues as well, right? So I mean, you add a goroutine, it definitely makes faster, but a lot of times what we have to do is we have to reduce the speed to get the memory under some bounded limit, right? So if you just keep adding goroutines, it would become fast, but then it also means that your memory usage keeps on increasing. So you might want to find a sweet spot between memory usage and concurrency.
Yeah, like for example, I think Ibrahim was talking about the stream framework. So we initially had 16 coroutines running on stream, and obviously performance was great, but then we realized that each coroutine, not that the coroutine was taking a lot of memory, but the work that we were doing in the coroutine required a gigabyte of memory for that work that each coroutine was doing. And so then we certainly are needing 16 gigabytes of memory to process this. So you have to just be just look out for these things, but it's a lot of fun to be able to to do things in goroutines, because things get extremely fast. Like whatever was taking, and recently we actually switched our test suite from a bash script to Go, and before we were doing everything serially, it was taking 35 minutes to run, and with goroutines now it's taking only 10 minutes to run the entire test suite. So concurrency is great, but you just have to be careful.
Do we have more questions?
There's a question about how do you debug goroutine leaks, and I think just because I mentioned that, it might make sense to tell how do you debug goroutine leaks. I think I would say like goroutines dump debug level 2 is the right way to do it, right? I think we even have a test somewhere, I think, Ibrahim, that you wrote in Badger.
Yes.
Checks the number of goroutines.
Yes. So if you want to have a very simple test, what you could do is I showed that there's this API called runtime.num goroutines, right? So what you can do is you could you could write a test which collects the initial number of goroutines. You do a bunch of work, and at the end, you could again compare the number of goroutines. So that API is called runtime, that runtime.num goroutines. So if you use this, you can simply figure out if you are leaking some goroutines. We have that kind of test in Badger.
I think there's a question about have you faced any race conditions and how do you debug them in case of any corruptions? Race conditions are common. And thankfully Go has a race flag that you can use for detecting those. I don't know what you mean by corruptions. I think memory corruptions, of course, probably. But I think if you once you deal with the race conditions, then finding those memory corruptions become easier.
Yes, and if you're using some block of memory incorrectly, let's say you're writing the same buffer reading, Golang does a pretty decent job of telling you that. So if you just run your test or build your binary with race flag, Golang will tell you that you're doing something wrong over there, and that would solve 95% of your problems, because Golang tells you that you're reading over here and you're writing the same value over here, which is not really right.
So we have
sorry, go ahead, Aman.
Yeah, so we have a follow-up over the concurrency. I mean, how end user over Dgraph can control the concurrency factor, and the follow-up is about the comparison with Kafka and Spark, where you can define the number of topics. And yeah, so the exact question is, I'm trying to compare Kafka stream that does parallel processing using how data is partitioned and everything. Can I do the same in Dgraph?
I guess the obvious answer is the simple answer is no. You can't really tell Dgraph how many goroutines to use. But I guess Kafka is probably not a apples to apples so comparison, because it's a very different beast.
Just one more thing. I think what you can do in dgraph is that all your data is started by predicate. So basically that level of like that level of starting and parallelism happens automatically. So you can have multiple dgraph groups which would be starting and storing data for different predicates. How Kafka does it in terms of like partitions and topics, if that's what you were looking for.
Yeah, so I think maybe a way to sort of understand how Dgraph uses concurrency for query execution is that each predicate or each field in the GraphQL query that gets you can think of it as a tree, and that's a branch in the tree, and each branch gets its own goroutine, right? So if you have, let's say, the root, and then you have 3 predicates that you're looking for, then there'll be like 4 goroutines, the main one, and then the 3 of its children. And then if they further branch out more, then we'll have more goroutines. So that's how we run each query. Now, this is different from Kafka because actually I don't know Kafka too well, so I can't really comment over there. But this is a very different beast because it's a OLTP workload that Dgraph is doing, right? Dgraph is a real time sort of database, and so our job is just to make sure the query runs as fast as possible. And in fact, we actually have a timeout. Is that like a minute or something? If a query doesn't run within a minute, then we time it out.
Yeah.
So yeah, I think that sort of like roughly gives you an idea for how concurrency works in Dgraph. But if you really want to tightly control how many goroutines run per query, then just ask for less data. I guess that's a way to do it. There's a good question about what's a good IDE for Golang.
We use all different IDs. Some people use VS Code. It's got some nice extensions. A lot of people use Vim, and we have built our own files for Vim, like our own config. And people also use Goland. So basically, whatever works for you. But we have people using all these 3 IDs here.
I think most people are using the VS Code, right?
Yeah. I think VS Code would be the most used one.
Yeah. And I heard there's a thing where you can run part of the VS Code on a server.
On cloud, and then
cloud.
you can also collaborate with different people. Yeah, that's also there.
Yeah. I don't think anybody is doing that right now, but I think most people are using VS Code, and it's nice because it has all of the Go tooling, right? The Go format and everything.
Yeah. And one good thing is that while you're using Go, it would also suggest you what to install, like what next thing you should install, like what's a useful extension and stuff. So if you're getting started with Go, I think VS Code is a decent choice.
Yeah, Vim is faster though.
Yeah. You can start with VS Code and slowly you can move on to Vim.
Good. We don't have any Emacs people here.
So we have one more question where participant want to ask when to use mutex over channels. Do we have some examples of mutex where they are more usable? Are there some performance differences, etc.? Anything?
That's a good question. We actually use both pretty extensively. One thing I would say about channels is that channels can get slow. Channels can get slow. So you don't want to, if you have, let's say, have a million things, don't put them in a channel a million times. We used to have code where we would, let's say, for example, we are collecting key values, and we were previously just pushing out each key value into the channel, and things were super slow. And we started to bash them up into a key value list, and then we would push out a list after it becomes, let's say, 64 megabytes of data, and that scales better with the channel. So basically you want to use channels, but you don't want to push too many items to a channel. You want to batch up the items if you have a lot of items and then push to channel. Mutexes are, I guess you could say the same thing about mutexes too, but mutexes are cheaper, I would guess, than, can I say that?
No. Channels also use mutex internally, but then
Yeah.
channels are specifically designed for passing things around, right? So you would use mutex and maybe
Yeah,
you have a
and
big
it's
buffer,
more
right?
around, right, and also I guess it's more around channel provider inbuilt thread safety, where while using mutex, it's more error prone in terms of handling the locks and unlock thing.
Yeah, they're serving like two different purposes, right? One is to like pass things to pass to the other goroutine, and the other one is just to synchronize certain portions of the code. Um, you know, and I mean, we use sometimes we use like mutexes and sometimes we use channels, and I think it's intuitive when you see a situation which one to use. But I guess like if you were to like kind of stand away and just try to like think about when would you use something, it's hard to like kind of imagine like why would you prefer one or the other. But like in a certain situation, when you're given a situation, you kind of like know what to use. I don't know if that makes sense. Probably not very helpful to like somebody who's beginning with Go.
So there is a question about, do you maintain any cache in your code like LRU cache, and how do you manage it to access concurrently? So we have Ristrato. So we have Ristrato, which is used as a cache. Ristrato is a concurrent cache, right? We use channels and then we have logged stores behind it, a logged map and stuff, which stores that information for us. So we have a concurrent cache, which is called Ristrato. It's on GitHub, dgraph.io/Ristrato.
And it's also like decently popular, right? Things got like 2,500 GitHub stars. And for people who might not know about Ristrato, it's inspired by a cache called Caffeine in Java, which is very well used across a lot of Java databases. And so we found that Go did not have anything as good as Caffeine, and so we spent like at least like 6 months building this cache within building this cache, and it outperforms. The last time we checked, outperforms any other Go cache that is out there, and also it provides better hit ratios. So definitely check out Ristrato.
We just crossed 100 answered questions, so yeah, just want to say thank you to everyone for asking questions and for keeping it interactive.
There's more questions. I
There's
think there's a
one
question.
question.
at the top, which is about will we be getting a doc with those for future reference? Um, would I don't know how Zoom
Yeah,
Q&A
it's
works.
possible. It's
It's
possible
possible.
in Zoom. We would get a text file and then we'll be sending it across to all the participants.
All right.
I just
Okay.
checked with Zenny.
There is one question where do we have any thoughts on test cases for concurrency use cases?
Um, yeah, I think one of it is actually even our used to be interview question, right? Um, you could I think in a test case you could like spin up a bunch of goroutines. Like for example, you wrote some code and you're not sure if it can deal with races good or not. So you could in your test you can spin up like 16 goroutines, and inside the goroutines you can do like 1,000 times 10,000 times the same action. And so the goroutines are sort of like going to race with each other to perform that task. And if you can catch a race, if you run with the race flag, then you'll be able to see if any race condition is going on or any deadlock is going on and stuff like that. But anytime you want to test concurrency, I think I would start with like 16 go routines and each go routine doing a bunch of heavy lifting, and that generally can figure out all of these issues.
I think we have more questions coming for Dgraph for Badger as well.
There's a good question about internship opportunities at Dgraph. Yes, I think so, right? Like we need people. We need people at Dgraph. We are hiring aggressively. So please do apply and um, you know, yeah.
There's a question about how can we calculate the maximum number of go routines that a machine can handle. Uh, like, would you like to take that, Ibrahim?
Go routines are actually very cheap. So, I mean, you could start a billion of them, right? So, but then again, it depends on what you're trying to do. If your goal is to just start go routines, sure, just use a for loop and you can figure out how many blind go routines you can start. But if your goal is to do some work, then you might need to run some tests, do some profiling to figure out what you can do. A machine can definitely handle more go routines, but the question would be, do do you want to start all those go routines? Do you want to use up all the memory or use up all the CPU? So that might be the right question.
By the way, I think goroutines are not that cheap. I mean, they're cheap, but they're not that cheap. So they cost between 4 to 8 kilobytes of memory each goroutine.
Yes.
And so if you have 1,000 goroutines, then that's like 4 megabytes to 8 megabytes. That's okay. But if you have a million goroutines, then that's like 4 to 8 gigabytes just for the goroutines, and that's probably not okay. There's a question about is there a repository for common concurrency sync algorithm implementations in Go? Example, bakery, deckers, etc. I'm not sure what these are. Do you guys have an idea?
No, I do not.
No, never heard about them.
All right. Do we have a plan for product or already have any service that works like Elasticsearch written in Go? Well, I think Believe is supposed to be the Elasticsearch in Go, but Dgraph also does like full text search and regular expression search and term matching and um, what else do we have in strings?
Uh, we can do term and text matching and regular expressions. Uh,
Right, and equality and hash.
yeah,
And then we for geo, we have password, we have
yeah.
uh, floats and date time and stuff like that.
Mm.
So we have a lot of indices in dgraph that you can also use. If because I think Elasticsearch, a lot of people use Elasticsearch for full text search. So dgraph also has that, so you could potentially use dgraph for that.
In fact, we actually have some users who also shifted from Elasticsearch. So people who needed join queries along, like along with some search capabilities, they actually found Dgraph to be a better fit. So you should give it a try.
We have one question where have you ever needed priority semaphores in Dgraph or Badger, like write operations having more priority than read operations?
I don't think we use them anywhere. We do have read write locks and stuff to do stuff, but I don't think we have like priority semaphores being used anywhere.
And Go doesn't have priority threads. So you could create something like that, but like but Go doesn't have the concept of priority goroutines. uh Maybe we go from the top, something for queue managements, Ibrahim.
Oh, sorry.
The question is there something for queue management?
Queue management, right? You could use Ristrato, no, but Ristrato will serve as a cache. So do we have something
I
for queue
guess it's like you
management?
use channels, right?
Oh, you mean, in Go. Oh, okay. So in Golang. Oh, sorry. I was this more of like, how do you do this in Badger or Dgraph? Oh, okay. Yeah, you could just use channels. Yeah, channels are first in, first out. So you could just use channels for that.
I'm assuming that it is like just in memory. I think if it goes on disk, then a queue becomes then it's a different thing, because then you have to like put it on disk first. But I think if it's just in memory, a channel should be doable.
We have one question, how did Dgraph perform in Jepsen test route?
Performed really well. I think the first one we actually found a whole bunch of issues and we fixed those over the year. That was in 2018, and then we did a follow up in actually this year, right, in February 2020. And I think Kyle, who runs Jepsen, could not find any more issues in Dgraph. We have some sort of like failures in transaction when we do tablet moves, and that was something that was pending on us. But tablet moves are pretty rare for us, so we did not spend as much effort there. But in terms of all the other scenarios around network partitions, machines crashing, clock skews, um, I think, and other stuff that Jepsen runs, um, there was no the Jepsen desk could not find any transaction violations. They also have linearizable reads. I think Dgraph worked through that as well. So it's pretty solid across all these tests. And by the way, I don't know if you know this, but Dgraph is the only graph database to have been Jepsen tested. And that sort of, obviously we are pretty proud of that. And I think Kyle actually had to learn a bit about graph systems to do those to write those tests. There's a question about, do you interview people on technology like on Golang, or do you take interviews on DS Algo? Yeah, we don't really tell people to know Go, but when they join Dgraph, we understand Go is relatively new, and so we generally interview on algorithms and other stuff. And maybe Pawan and Ibrahim, you can probably like talk more about that.
Yeah, we basically focus more on DS and algo. We see that if you understand algos and if you're able to know which data structure to use when, so that's our focus. And we are not looking for those problems that you would solve on one of the websites. We look for more of the problems that you would solve in like a real world scenario. So that's the idea. And we are agnostic to the language that you use, as long as you can use one of those object like one of the languages like C++, Go, which are statically typed. We are usually good, or even the dynamic
Also,
data.
yes, we also allow the candidate is supposed to write code in their editor, and they're allowed to use Google as well. So we understand that people do not know everything, as in all the APIs, and that's perfectly fine to use Google, but we expect them to write runnable code. So they're free to use the language they like, the editor they prefer, and use Google for whatever they need, but they're supposed to write runnable code in the interviews, which is what people at Dgraph do as well.
We have one question. So just like ELK, do we have something similar using Dgraph for logs management and dashboarding?
We
Um,
actually we
okay.
had a dashboard on Grafana. Like we have a dashboard that you can use on Grafana, which can show you some of the metrics about the number of requests and the latency and stuff. So we have that, and for logs, you could use any logging solution. Like we support the logging formats like JSON, so you can just parse that and use that with any logging solution and get your information.
Like I guess ELK does like log collection and stuff, right? And search. I mean, Dgraph doesn't
Yes.
do that.
Yeah.
Um,
So I think that's
yeah.
Elasticsearch, Logstash, and Kibana. So we don't do the log aggregation, but you can use any software because we support all those formats, which are the common formats, and then you can use a Grafana dashboard for getting metrics out of those.
Yeah. And I think for folks who might not know, so Dgraph uses Google log library for logging, which we found to be pretty efficient. We had tried other logging libraries before, and ultimately once we saw this one, this stuck because it was pretty efficient. Um, and so I think that generally works well with a bunch of other softwares.
I guess this will be the last question. So for calculating the system requirements for a Golang application, let's say while running it on a Kubernetes pod, is stress testing the only feasible option?
Do you want to take that up, Ibrahim?
Sure. Again, there's no easy way to figure out, right? Let's say you're writing dgraph, the memory usage of, let's say, dgraph or badger depends on what you're doing, right? So you would stress test it and it would tell you that it needs maybe 30 GB of memory, but that doesn't really give you the correct idea of how much memory it would need. I mean, the only way to figure out would be to run the kind of workload that you would actually run while using the system. The only way to figure out how much memory would it need with your workload is by running your workload. So you could again stress test it, but then that stress test would give you skewed results. So if you just bombard data, then again you would see maybe high memory usage and stuff. But then it depends on your workload. So if you're going to run X type of workload, you should test dgraph, test badger with that kind of workload, and that would give you a right idea of how much memory and how much performance you would expect.
I think one thing to add there is that if you, and I'm going to talk about that tomorrow. So if you were to do manual memory management in Go, then you can get a better idea about like how your memory is being handled. Um, and there then, like for example, what you could do, and that you can do even with Go's memory management. um, you can track the memory used by Go, and if the memory goes above certain threshold, you can stop taking requests to the system, right? So that way is like the system would have some chance to decrease the memory usage before you start taking requests again. um, and I think in other production systems I've seen server switching to what they call lame duck mode, and in dgraph we call it the draining mode, where we would not take requests anymore. We would just be processing existing requests and let the system stabilize before taking more requests. So you could do things like those to deal with if there is spike in memory usage because there's something going on in the system which is taking up a lot of memory. So you know but as Ibrahim says, like there is no real um, short answer of this is how much memory my Go program would take. It just depends upon how much work it's doing, right? If you do work slowly, it will take less memory. If you're doing a lot of operations, it could take more memory.
We have one more
There,
question. So yeah, go ahead, Ibrahim.
I noticed someone asked about how can concurrency degrade performance. I have tons of example of that. I mean, it's pretty easy to show. Uh, you just, if you have a lot of small routines, let's say you have a routine that does some work which is very fast, you start 1,000 of them and you would notice that 1,000 go routines work slower than 4 go routines. You'd be wondering why, since you have concurrency is supposed to improve the performance, but it's important to understand that the scheduler also needs to do more work. So if you have 1,000 go routines running, the scheduler needs to schedule them. It needs to context switch them. So if you blindly just increase the number of go routines, that would never translate to just linear increase in performance. It could degrade the performance after a time.
We have one more question. So does dgraph has a query planner like normal SQL databases?
Dgraph currently does not have a query planner. It's something of sort of, it's on the roadmap for us to build one. Thankfully, compared to SQL, which is a very English level, English style sort of query language, which doesn't give you much information about how it should be executed. GraphQL is a lot more structured, and so you have a pretty good sense for like how you would generally want to execute it. Now, I think there are certain cases where you want to optimize it to be done this way or that way, and that's what we would tackle by having a query planner. But I mean, Dgraph is already performing pretty well without having a query planner so far, um, and that just shows the power of GraphQL as well.
I think we have covered all the questions.
Awesome.
Can we tag these questions as answered? I think Pawan and Aman. And there's a new question which says, we followed similar approach of throttling and error handling for concurrency in our code, though we didn't create any custom type for that, and was not aware of these packages. I think one thing I've noticed is that if you see some pattern happening repeatedly in your code base, it's always a good idea to create a custom sort of class for that, a custom package for that. It helps a lot standardize things. We have done that repeatedly in the Dgraph code base, and that's why we have Closer, we have Throttle, we we built Stream, um, and we have like plenty of other um, small functions like this. The check function, the what do we have, like assert true. So there's like small things that we added, which we then just use across the code base, and it allows for a simpler code base to understand, um, and also makes it more robust.
There's a question that if you have a single core machine, then does go routine make any impact?
Yes,
Yes.
goroutines are multiplexed. So a goroutine does not, a single goroutine, a bunch of goroutines will be multiplexed, right? So there would be context switches, and Golang runtime will try to multiplex a bunch of them into a single thread. So you would see better performance even on a single core machine.
And a good example is, let's say these routines are just reading data from disk, right? So if you were to just run them serially, one after another, they'll have to wait for that entire time when they're reading the data, right? But if you had coroutines, then the moment they start to block for data read, Go can put another coroutine in there, which can then start processing the already read data, and things can go much faster. So, so depending upon what you're doing. But on the other hand, if you're just doing completely CPU processing, if you're just churning some numbers, completely memory, not touching the disk, not touching RAM, not touching network, then you might not see as much performance gain, because um, for a pure CPU operation, more coroutines would not help on a single core.
There's a question for you, Ibrahim, that if you're going to discuss your implementation of Skiplist, would there be a continuation about your implementation?
We would definitely we could talk about Skiplist in one of our community calls. I'm not sure about continuation part. So, but yeah, we can definitely talk about the Skiplist implementation that we have.
Initially, we decided to talk about Skiplist, but then we thought that it might be too much information for this workshop. So that's why we kind of restricted it to things that we could cover in an hour. But yeah, we would love to have another call and share our implementation of Skiplist.
And we have Dgraph community calls, right? We have it every
Mm-hmm.
month.
Yep.
So we could potentially cover some of these topics in the Dgraph community calls. And there's a lot of like knowledge that Dgraph team has in terms of, particularly in terms of like how to do systems well, right? Like concurrency, Go, scale, performance. In fact, we probably have like more we can talk about than we have time to talk about. So, you know, so I think maybe we can use some of those calls to like share some of that knowledge.
There's one more question to get hands on to Dgraph open source. Oh, I think it's answered already. I was reading it and I think Amar answered it.
Yeah. So yeah, the question was, how is it to implement dgraph, and how easy it is to enable the debug performances with Prometheus and etc. So is the documentation detailed and everything.
And this was an example of a real life concurrency bug. That's what we were going to, and that's what we showed you guys as well.
It was a race condition because there was not enough mutex locking.
Yeah, that's where you use a mutex lock. Someone was asking, right? Don't use a channel there, use a mutex lock.
I think the question, if I remember correctly, was about how is it to do debugging using existing sort of like what kind of things that Dgraph has to allow for debugging. And I think Dgraph does a lot of like things, right? We have metrics which can go into Prometheus. We always turn on profiling, so you can always profile a Dgraph program. You can do CP profiling, memory profiling. You can do open sensors. There's open sensors integration, so you can do tracing of your query, so you can see which query part took longer, etc. Similarly, you can do traces of your mutations, the writes. And we use all of these things to like better understand the performance of Dgraph and optimize the performance. Yeah.
Are there any more questions? We have also shared if you see the chat, then you would also see a link for the survey that we have shared. So if you have any feedback that you want to give to us, please feel free to go through the survey link and give us feedback about this workshop and how we could improve it.
There's a question about will Dgraph move to OpenTelemetry? I guess so. I mean, I think we'll have to eventually move. I think we are probably just buying time to not have to, because the open sensors is so deeply integrated at this point. It would just take us a bit more work to like switch over to OpenTelemetry, and we just haven't done that yet.
Well,
I think that covers all the questions we had. I don't
just
see
wanted to thank all of you for attending, and also wanted to share that we have the big conference coming up tomorrow, and there are a lot of interesting talks for you to attend, and I'm sure that you'll learn a lot from those talks. So definitely tune in tomorrow for the talks on the conference. Yeah, it was great to have all of you here, and hope all of you learned something new today.
And for folks who might not know, the link is systemsconf.io. Systemsconf.io. So you can go register there. We already have like 8,000 registrations for the conference. We have an amazing line of speakers. Some of the most known people in the Go performance area are going to be talking. We have Daniel Lemire, the professor who has written a lot of research papers about getting great performance using SIMD instructions with Go. He did rolling bitmaps. He's done SIMD JSON. We have speakers from Minio. We have speakers from CockroachDB, PingCap, TIDB. So all the folks who are and other folks that I'm not even like remembering right now, but we have a lot of like interesting talks, and this is different from the typical Go conference in the sense that we are pushing Go to the limits here. So we might be giving you advice which is probably not what you would hear elsewhere. Because when it comes to like pushing a language to the extreme, you have to do things which you typically would not do. So it would make for a very interesting conference. If there's one conference that if you want to like really bump up your Go skills from, that this is it. So hope you see you all tomorrow at the conference.
Thanks everyone for joining. We had a lot of interesting questions, and I'm glad we had questions.
Thanks everyone.
Thanks guys.
Thank you everyone.